Trouble with polymer physics, sustained orientation. Groundbreaking experimental research shakes the current understanding of the liquid state of polymers. This is the video clip lecture number 1 from the New School Polymer Physics. The title is inspired by a book I have recently read from Lee Smolin entitled The Trouble with Physics: The Rise of String Theory, the Fall of the Science, and What Comes Next. And this book is very interesting because it shows how a dominating theory can benefit progress in science, but also can slow down the introduction of other theories. The domination is such that it may become a dogma with all the negative consequences on future research that a dogma can entail. In fact, if you take that book and replace in chapter 1 the word string theory and replace it by the reptation theory, you will see a great analogy with polymer science and the domination of the reptation theory on polymer physics and its limitations, its rise, which has of course dominated the last 40 years ever since De Gennes introduced it in 1971, but it started to be celebrated through the work of Doi and Edwards in 1979 in a famous paper, and therefore from 1979 on, still now, up to now, the reptation model has been the dominating teaching theory, which explains or has tried to explain the features and physical behavior of polymer. And as you will see in the following presentation, there is perhaps in this presentation of the new experiments some challenge to the current established theoretical model of entanglement, which might draw it down to its fall. And this is the debate which I am starting to trigger, and this first video clip lecture is the pretext for doing so. The log viscosity versus log of molecular weight is a classical presentation of the concept of entanglement. The entanglement is seen here as the break in the curve at a critical molecular weight called m sub c, from which the slope of the log of Newtonian viscosity versus molecular weight passes from 1 to 3.4. There is a large increase of the effective molecular weight beyond the molecular weight for entanglement, or the critical molecular weight. And what I am concerned with, what started my research on entanglement, and is the following. If you extrapolate the data, if you extrapolate the line below the molecular weight MC, you see this called disentangled state. And is it possible to obtain a partially disentangled state such as B1 for a molecular weight which is the same for B2, B1, and B, B2 being the disentangled state, B being the normal entangled state, if I have succeeded creating a B1 state? First of all, therefore, I need to address the fact that is it possible to process such a state? How does it return to either B or B2? In what time? Is it following the kinetics dictated by the reptation model? And is the final state the B state, or can I have some processing conditions which bring B1 such that the final state, the return state, is B2? Or alternatively, is B1 stable? In other words, in this research we're concerned with the stability of entanglement states. Now let me introduce you two modes of processing which are currently being used, especially the one illustrated in this figure called shear finning, in processing. For processing melts, the increase of the strain rate, the increase of the speed at which we make melts flow through capillaries or through gaps in mold injection molds, for instance, is known to create a decrease of viscosity, as illustrated in this figure. The log of viscosity is seen to have a plateau at low speed, low omega, which is the frequency in a dynamic test, or gamma dot, which is the derivative of the strain, so the strain rate, if you want, which relates to the throughput or the speed at which the layers are moving in the flow directions. This is a classical view for someone who is in rheology, and the Caro equation describes this pretty well. The plateau is the Newtonian on the left hand side, Newtonian viscosity, and the material shear fins, meaning this viscosity decreases as we move towards a higher strain rate. Shear finning of plastic melts is of course known to processors and is used practically to lower the viscosity of melts during the filling stage of injection mold by increasing the speed of injection piston. This is particularly useful in the case of thin wall injection moldings, for instance in micro moldings, when you have extremely small parts to make, where considerable forces are required to fill the mold because the viscosity of the melt, when the viscosity of the melt remains quasi-Newtonian. In summary, shear finning is well defined analytically and used practically. Now, what other parameter can one use, to decrease the force required to flow? A polymer melts, and therefore, of course, the flow or the fluidity depends on its state, which is function of pressure, function of temperature, of course, and, as we just saw, of the strain rate. At larger strain amplitude, for instance, of oscillation, suppose I'm oscillating the melt, say transversal to its flow direction. We will see that in a couple of slides, the way I can do that. But if at larger strain amplitude, so-called in the nonlinear viscoelastic range, the strain amplitude at low frequency induces strain softening, which is the domain of the large amplitude oscillation experiments, typically 1 Hertz. And if one uses higher frequency, as we will see, strain softening becomes time dependent. This phenomenon I call real fluidification. In other words, to describe strain rate effects, we'll still use the classical term shear fitting, but if we couple strain rate or frequency and strain effect, we call that real fluidification. Here is a couple of examples of strain softening in a rheometer at constant frequency, so PMMA, and the frequency is 250 radial per second, and the temperature is 230. Recall that Tg is 105 degrees C, so it's far above Tg. And I am plotting G prime and G double prime versus the strain. So I am increasing the strain. The first point that you see on the left are the classical linear viscoelastic range, but as gamma increases, one sees that the G prime and G double prime values decrease, which is different phenomenon than shear thinning, where G prime and G double prime continue to increase with gamma dot or omega, but the rate of increase slows down with an increase of gamma dot, which is shear thinning. Here the moduli G prime and G double prime decrease with gamma, so it's a different phenomenon, of course, strain softening. If you look at the G star, the dynamic modulus, the combination of G prime and G double prime, you of course have this decrease with strain, and of course the viscosity, which is the ratio of G star by omega, omega being constant here in this case, the viscosity will decrease. So it's another way to decrease viscosity in addition to shear thinning. Let's now look at what we said was a special range of combination of frequency and strain for which we observe real fluidification, where the viscosity becomes time dependent. And this is illustrated in this slide, which is showing on the top the history for frequency. So there are 3 steps. First step is in the linear viscoelastic range, and you can see that the conditions for frequency, and as you will see below, for also strain versus time, are going to be the same at step 1 and step 3, the recovery so-called, and they are in the linear viscoelastic range, meaning small strain, here it's 1%, strain, and small frequency, here it's 1 radial per second. And now in step 2, we are doing two things. We are going to shear fin the melt, so increase the frequency. Here you see that as a step function we go up to 47 radial per second, and at the same time I am increasing every 2 minutes. I am increasing stepwisely from 5% strain up to 25% strain, in this case the strain percent, and then I am studying the recovery curve. In other words, I'm going back to the initial conditions just to see what happens to the melt. This is what happens to the melt, plotting viscosity versus time for the 3 steps from left to right. You see that the before treatment, so-called, I have for that temperature a viscosity of 57,000 for that melt, and it stays up there until I change the frequency to 47 radial per second, where there is a drop, immediate drop of the viscosity to 10,000. And as now the strain increases, that viscosity remains constant until approximately 20% or 15% is reached, and then I see a drop of a viscosity in time. So the viscosity becomes time dependent in what is called the treatment zone, and finally I get a further reduction to about 3000 pascal second, and I call it the processor viscosity. So we have a huge drop of a viscosity from 57,000 to 3,100, and 3 times less than the shear finning viscosity at 10,000 is caused by strain softening, time-dependent strain softening. What happens if I just reverse, as I said I would in step 3? I reverse the conditions back to what was in step 1, low frequency and low strain amplitude, and there is an immediate jump of a viscosity to 38,000. Well, this is not 57,000, so it does not return all the way to the initial viscosity, which would be the case if the material was just shear finned. It will just springingly go back to the same value it had. Here, because there was this coupling with strain softening, and especially time-dependent strain softening, you see that the recovery occurs in 2 steps. One fast one, and then a slow recovery, which is taking time, and which we'll study here, and which we question the origin of this phenomenon. Okay, so the real fluidification is observed here, and we are going to understand, or try to understand, this phenomenon, which I can already mention to summarize is due to the entanglement instability caused by the passage in the rheofluidification state. So this talk is about this question: can one use rheofluidification to modify the state of polymer melts? That is, create and stabilize non-equilibrium liquid states. Can the viscosity reduction of a melt be preserved in a pellet? And third, is there any practical application? Now, the last question I have already answered partially in several video clip lectures available in this VisiQ panel. And of course, there are applications to the fact that if you succeed decreasing viscosity of a melt, or create a grade which is inherently the higher fluidity when you reheat it, it's obvious that you have main application in many areas of polymer processing, especially film packaging or injection molding, lower temperature or lower pressure during processing, etc. And of course, if you mix with nanotubes, carbon nanotubes for instance, and create batches, you can use higher concentration for the batches if you are lowering the viscosity. All of this I'm pushing to the side for this introduction, and will not describe further. What I have designed and built is a real 3Dification processor. This is described in recent articles in 2013 in Journal Micromolecular Science Physics, but let me give you a few comments about this. And that is the first generation which I built. I am now using the second generation, which I call Pink Flow processor, which has different features, but let's concentrate on the first generation. This consists of an extruder feed on the right, which goes and put the melt into a gap, the gap being shown here as the space around a cone core, which is rotated and vibrated through the action of a motor 1 and motor 2, as you can see on the left. So the cone which you see inside is the rotor, and it's a conic expanding the flow from the inlet to the outlet. The outlet is on the side, you see plastic out, and all the rest of the mechanics is just to make the inner rotor rotate and vibrate. The outside, the stator is cooled and heated, and so that the melt can flow through, and defines a gap which is between approximately 1 millimeter to 4 millimeter. Of course, the cone can be actually moved to increase or decrease the gap. Okay, so that's the way this thing looks. Here is a picture of the first prototype machinery which was built around this concept. You can see the extruder feed is on one, the machine of real 3Dification processor itself is on two. There is a the melt is coming out on the side. 5 is the electronics with a computer which directs the motors and the and controls the temperature of different zones in the real 3Dification processor. There are 3 zones. You measure temperature in those 3 zones and the pressure along the flow, and you see here at number 4 there are the two motors, and 3 is a universal joint which can be dismantled so that you can disconnect or connect the action of the 2 motors to the to activate the rotation and vibration of the inner cone. Here is an inside view of the cone region. You can see the melt flowing from left to right, and we will describe those little pits that you see, the ribs, which are in both surfaces of the stator, number 13, and 14 is the water. So on both sides you have these ribs, which we call intelligent ribs. You see also the melt flowing through the gap, which is here number 3, and 8 are heat bands, and 15 are cooling channels, so that the heat can be removed from the first site, so the melt is temperature is controlled. Okay, and in an option, you have a possibility to vibrate externally the inner mold, the cone, but you will see that you can rotate it also without vibration, and the ribs, the action of the ribs, which rotate with the rotation of the axis, will create the vibration. I'll discuss that in a minute. These are description of the intelligent ribs. As you can see, they look like tracks, train tracks, and the vibration is created by the rotation, and the angle of the tracks create helicoidal flow, and also depending on the pressure flow component, and you have also the passage through the wall. The wall is tilted. The track heights that you can see below as with a height h sub r. The track width is small l, and so forth, and all these are designed precisely, machined to correspond to a melt configuration which apply to the nature of a polymer flowing in. And we study that with a dynamic rheometer, so that we know how to pinch the melt, how the melt reacts to expansion, how it reacts to stretching, by studying with a linear a rheometer, stretching rheometer, how the melt viscosity behaves with a strain rate, and also with in shear mode we determine how the melt behaves in pure shear, and we then create a simulation introducing all these parameters into the simulation, so that we have a vibration created when the melt flows through. As you can see, the melt is being extended at a periodic time, and also it is so vibrated by the fact that in between the ribs the melt can relax, and the height is varied since there is a rib on both surfaces, on the water and on the stator, as I said before. There's a picture of the cone and of the barrel. You see the inner side of a barrel also has the intelligent ribs design, which faces, for a given gap, the design on the cone structure. This picture, which is a CATIA drawing, shows that we vary the width and the angle of tilt of the intelligent ribs, and the tracks look different as you move up on the surface. This is done by computer, so you can basically vary and create different types of surfaces and see the difference on the melt flow. Okay, so it's very flexible, but this has the advantage of creating a vibration from the inner rotation, which has no seals, and the melt is still vibrated. So this has many advantages over the triggering of vibration from external means. Of course, in this design here, we have both the ribs and the external vibration to test the effect of either way to vibrate or combining the two. Okay, I will discuss that also in a few slides. This is showing that the parameters, the rib geometry, the angle, the spacing, the base ribs, the rib volume, the length, etc., and position at different position. You have the cone itself, which is sliced into sections with an index 1, 2, 3, 4, 5. You see up to 19 here, and for each section we can determine the ribs size, the ribs dimensions, and the width, and change it. We also can, this varies of course, and determines the amount of extension on the melt and the amount of vibration, not only longitudinal vibration across the walls, the track walls, but radially along the track itself, since we have the height of the ribs to determine an acceleration between bumps. Okay, so for a given throughput, we know exactly the radiological combination of strain and strain rate, not only for shear but extensional radiology. And we have also a variation of the number of ribs per turn, which determine the frequency. So as we move along, of course, as the cone radius increases along the flow, we have also an increase of the amplitude, therefore of the strain of the vibration. Okay, here in this slide we show the effect of the design of the intelligent ribs, and the fact that it is equivalent to adding an external vibration is demonstrated in this slide. So we have a viscous torque as measured by the amperage, the intensity of a current to turn the inner cone with a given melt at a given temperature, flowing with a given flow rate from the extruder, a given feed. And we have several cones which we have built, so here we can compare cone 1 and cone 2. Cone 1 is without ribs, no ribs, and as you can see here, if we apply only rotation, we have in steady state a certain value of the viscosity, meaning of the torque, and that value is about 18 ampere. Okay, if I add vibration to the rotation, I have, for the same cone without ribs, I have reached the level 1V. So we have a benefit of increasing the shear, the shear and the strain rate through adding vibration, and we can see that by a lowering of the torque. So this is a boosted shear fitting, if you want. That's 1V. Now if I put ribs on both surfaces, facing surfaces of the barrel and the rotor, I see that with just pure rotation, this is curve number 2, I obtain in steady state a value which is equal to 1V, as if the vibration was created from within. And that's what I said. I said that the set of intelligent ribs created vibration from within, without the requirement of using an external motor, and this is proved here. Of course, there is even more to say, but I'm not going to describe this in this presentation. Is if I combine the external vibrator 2V is a curve with the ribs included. I still increase even further the reduction of viscosity. So now I have reached a level of approximately 6 amp compared to a value which was 25 at the beginning before rotating the melt. So a melt which is extruded but not rotated, not vibrated, with no ribs, as an amperage and a viscosity of 25. And of course you can see the effect of first the rotation, 2 the external vibration, 3 the ribs on the surfaces, and the combination of all brings the viscosity to 6, about 5 times less, 4. Now, all the benefits of a previous design for a real fluidifier can be seen, as I said, by a lowering of the temperature processing. I can lower the processing temperature of a melt by approximately 100 degrees and still have a melt which is flowable. I am describing this in the papers described at the beginning in the journal Micromolecular Science Physics. There's a couple of papers on radiofluidification. There's also a large benefit on the pressure. Of course, if you reduce viscosity for a given throughput, you are decreasing your pressure, and that pressure could go from 4,000 psi to 400 psi, so factor 10, which of course you can use to increase the throughput and not endanger the pressure, the process itself. So these being said, and I'm not insisting on that, I'm going to talk about sustained orientation, which is created by coupling 2 real fluidizer 1 and 2, here yellow and green, and I have done it in this particular configuration. So you will recognize the real fluidizer 1 with extruder feed and the 2 motors M1 and M2. It has of course the ribs and so forth inside, the cone, the expansion of a melt. And 2, instead of having an output to a pelletizing line or to viscosity, I'm using a second real fluidizer, and with its own motors, with its own temperature controls, and it has a gear pump in the back, the outlet, and a viscometer. And also coupled with that, but not shown, is I can pelletize a melt while its viscosity is being measured in parallel. So this is the equipment which I call dual real fluidification processor, which I've used to create the non-stability of a melt, which is sustained for a long time, and which has been which we have been able to preserve in pellets, as I will show. Now this is of course a special, also I should add that in the rotation of the cones, there are 2 cones, real fluidizer 1 as 1 cone and the real fluidizer 2 as another cone. And in the particular examples which I will describe, the rotation in the 2 cones is reversed. In other words, it's counterclockwise in the first one and clockwise in the second. And you will add, you will ask me, does it make any difference? And I will just say yes, it does. Surprisingly, it does. So this being said, let's move to determine a little bit more what we can of course simulate what's happening, and put in the program the stages for the dual stages, the dual processors which are coupled, and I am for instance describing what happens to the melt. And what you see here is by checking the volumes where the melt flows in, we can determine the residence time, and the total residence time here for this particular melt is about 10 minutes, and it is being treated in the pink zones. Treatment 1, rotation, no rib, rotation, no ribs, rotation, no ribs here, and so forth. Well, in this particular case, no ribs, but in the examples which I will describe, there are ribs. And then you have recovery, another treatment, another recovery, and we see on the column next to it the times for each. So we see that there is some recovery occurring after treatment. The treatment creates rheofluidification conditions at a given temperature, and then there is some recovery, which is the passage of a melt through the end zones to reach the next processor. And finally, before it being measured at the end, before it goes into the viscometer, the same thing happens, is that the melt is no longer treated, no longer rotated. It is simply flown to the exit zone without treatment, so it relaxes, it recovers. For how long? Well, in one case it is approximately 2 minutes after the treatment 1, and then in the next one you see 0.186 plus 0.45, 0.59 and 0.12 minutes. So it's another approximately 2 minutes and a half. So we have to take that into consideration when looking at the results, because it's important to know that we expect to see and measure a viscosity change while rheofluidification is active. In other words, in the treatment zones. We should see that, and we see it in the when we measure viscosity from the torque and from the pressure sensors, which are positioned along the flow directions. But recovery is no treatment. There's just flow. So the melt is transported, being pushed, if you want, and is moving by just the pressure flow, which pushes the melt from the exit of the treatment zones towards the end of a melt. Okay, and we see that it's about 2.5 minutes for that time. Now, if you look at the existing understanding of flow and melt being determined from its value of viscosity at a given temperature and pressure, it is in a rheometer we determine what is its longest relaxation time, meaning that it has relaxed totally from any previous deformation if we rest the melt for a time longer than the longest relaxation time. And this time is called the reptation time, determined by the reptation theory, and it is tau sub d, and we know that the crossover point of G prime and G double prime is a good way to determine its value. So here we see that this for polymethyl methacrylate at 230 degrees C. So again, it's 125 degrees above Tg. The recovery, the reptation time, is indeed very small. It is 5 milliseconds, 5.12 milliseconds. So what do we expect to see if we have a melt which is treated in different zones but then relaxes for recovery times of about 2 to 3 minutes after the mechanical treatment? Well, what we expect to see is a return to equilibrium of all the deformation process And in what time? In 5 milliseconds. So in 2 or 3 minutes, which would be 180 seconds, so it's more than 100,000 times longer than the longest relaxation time. We should not see any difference if we position a rheometer, a capillary viscometer, at the end of a process. And actually, in most of the experiments that we do not see any difference. In other words, you agitate the melt, you make it pass in different things, you vibrate it, you heat it, you stretch it, you do whatever, and you don't see any difference at the end in the rheometer position at the exit, except for certain conditions of frequency and stretch and gap and temperature and certain synchronicity between the treatment 1 in the rheofluidification 1 and in the treatment 2, rheofluidification 2. Then you see at the end in the capillary viscometer, you see that you have succeeded sustaining the viscosity drop, which has been observed, is always observed under the treatment zones. It is now affecting the melt in the long run, and you see that in the viscosity meter by the pressure you see in the middle graph here. Here, this is a EVOH example. So this polymer EVOH is at temperature 200 in the viscometer, capillary viscometer, and we observe a steady state at 300 pressure Pascal, and this corresponds to viscosity about 3000 Pascal second. And as you can see, at a certain processing time, the technician using his computer changing all the different parameters for vibration, amplitude, gap, and temperature has succeeded triggering rheo conditions which are creating sustained orientation. Sustained orientation is, as you will see, is not only observed here in the viscosity at the end after he has passed 2.5 minutes in the exit. It is still visible, and so the melt is getting slowly to conditions where it remains at a lower viscosity, here 1000, so it's 3 times less. And basically we see that in the capillary viscometer position at the end. This is another example for the PMMA at 230, and you can see that the viscosity normally is 1200, and then the technician has found a zone where that can be reduced to approximately 650 Pascal second, and then he found another improvements. So by combining the rheo processor in zone 1 and 2, he found another stable drop of the viscosity to approximately 500. So 1200, 500. This seems to be steady and stable. So if the processor leaves the machine the way it is, it will stay that way, and we can pelletize the melt which is obtained. We know that these conditions are going to result in a modification of the state of the liquid, which when frozen will also get us a new kind of grade where the melt produced is going to be unstable. So it all depends how long does it take for the melt to recover, and this is what I will show you in a few slides. So first of all, those pellets created and which were measured, the viscosity measured in line So you have an inline rheometer giving you a certain value, and as you can see, the value was 1200. Here, this is the PMMA, and it's 1200, the normal value corresponding to melt index of 17. So melt flow index for the untreated or with no sustained orientation is the bottom values on the right hand side of the curve. And now we have succeeded obtaining melts with a various type of modification of the MFI, and this is also observed by a melt which has various inline rheometer values, and you can see that I am at 500. That's the case I've shown you, and but all the melts in between were also obtained and correspond to a value of MFI between 17 and 40. So I have succeeded obtaining in pellets a sustained orientation, which is a melt which is no longer if you want, a stable melt, or at least it's stable long enough that I can measure the differences, but this melt, as we will see, loses little by little its stability, tries to return to the initial value of entanglement that it had in the virgin sample, untreated sample, and it takes a very long time. So the understanding of what we are describing from the established theory is non-existent. Where do we see in the current models understanding polymer physics that we can create unstable polymer melts? We knew that we could create unstable glasses. The works of Kovacs in the 70s or 60s shown that we can quench a glass from a melt into states which are under non-equilibrium, and Kovacs has studied with several of his colleagues the return to equilibrium, but the melt itself is supposed to be in equilibrium, and then we are saying here that no, we can create unstable or non-equilibrium states for the melt, which themselves require the study of the time to recover, just like the recovery of a glass towards the equilibrium state. Here we can destabilize the entanglement. That's what, at least the assumption that we advance, is that we have touched what is actually the entanglements of a melt, and we have destabilized the entanglement to the point that the melt stability is different, and it takes very long time, or it can be a short time. It depends the amount of so-called disentanglement we have done, and the sustained orientation and the time it takes for sustained orientation to recover, in other words, to disappear, is also a function of a structure, function of the structure of the entanglement state, and function of the attractions, if you want, or coupling between all the types of bonds, the van der Waals bonds, the hydrogen bonds when there are few, when you have polar molecules, and etc. So the organization of all the interactions between the conformers creates what we normally describe as entanglement, what the theories, admitted theories, established theories call the reptation or the tube, describing the interactions in the entanglement state. In this case here, we have succeeded getting new states for the entanglement which are no longer described by the longest relaxation time, which are described by much longer times, and we attribute this to a different definition of the entanglement network itself. What I said here is compare for PMMA inline rheometer readings of a viscosity versus the MFI, melt flow index, values obtained for pellets from the same melt after cooling and pelletizing. So basically what it says, the pellets have captured the viscosity drop which is observed in the inline rheometer, and are and that I can create a stability which is beyond the reheating in the MFI instrument, which takes 5 minutes or 10 minutes, and then I push the piston to measure, and then it takes another 2 to 3 minutes to make a measurement of MFI. So at least this 10 minutes there, the melt is indeed trying to recover, as we will see, but it's taking such a long time that I am capable of capturing still a viscosity decrease, which was done through orientation within the rheo fluidification processors. Here is another polymer, polycarbonate, where we observe the same thing. There's a correspondence between what we observe in the inline rheometer and between the pellet MFI measured. And as you can see, I start from a pellet which is at 14 in the MFI index, and I'm going to 40. And we observe a change, a drop of a viscosity from 350, 340 to approximately 160. So we don't have, we know that we're losing some. In other words, this is just a process which we are observing as it continues to return to a more stable state, and so we know that we are losing some. The know-how of sustained orientation is to know what is the speed of recovery, so that it can be useful. How much do we need to torque and under what conditions within the rheo fluidification processors in order to increase the time of recovery such that we can observe it. That is a problem of physics, because we need to understand the network of entanglement. We need to understand how the network of entanglement, or the state of the entanglements, is defined physically by the interaction between the bonds, and how this correlates to the enthalpy and entropy of the molecules. The enthalpy should be responsible, we say, to the sustained orientation, and not just the entropy. If it was just the entropy, we know this process. It's used in the heat shrink process, and as soon as the melt is positioned at a temperature above motion, we know that whatever deformation was imposed is recovered very fast. So we know the entropy, but what we're doing here is coupling the entropy and enthalpy of micromolecules in a way which influences the network stability, and the network stability, of course, determines the real true time to return to a stable entanglement state. Here are some values obtained for what we call, therefore this property is called sustained orientation. You can see that for polycarbonate, for instance, we have a virgin MFI to 12, and which goes to 21, PTG 8 to 12, 50% fluidity improvement, LDPE 140%, polystyrene 50%. This was all value. It's actually more now, recent, with new fluidification design. We have improved these values, but let's keep that to the first generation, which I've shown today. For PMMA, from 17 to 37, 118%. Note that I said MFI after treatment and correction for MW change. There are some collateral effect if I work at high temperature. This is inherent to plastics. If you treat plastic into a twin screw or a single screw, there is a certain loss of molecular weight which is inherent to processing it at high temperature. So if there is any molecular weight change, I need to take that into account when I calculate the flow improvement, because I do not want that, as we know, the molecular weight also has an influence on the viscosity. And well, this was the first slide. I show that, you know, it's a factor of 3.4. So it is very sensitive to a molecular weight change, and I need to correct for this in order to determine what is coming from the process of destabilizing the integument network. Okay, so the sustained orientation is observed when the melt can preserve for a long time its non-equilibrium state created by processing conditions which modify the integument network and its stability. As I said, I am measuring for each sample treated. I am always doing a measurement of the not only viscosity of a melt flow index of the pellets created, but also the GPC of those pellets created, and I am comparing with the normal extrusion, or I'm comparing with a virgin. And in this case here, this is a normal extrusion with an MFI 14, and then I'm comparing it with a disentangled polycarbonate disentangled. It's quote unquote. It is that means a Rio fluidified processed. Okay, and I see that the MW is pretty much the same. The height molecular weight tail is also the same. There is some changes in the low molecular weight tail, but if we really compare and see whether it could have a plasticizing effect, it does not. It would basically correspond or explain 5% of the results that we are showing, and not the 118% flow improvement that we see for PMMA, for instance. Plus, you would not see a recovery. In other words, as you will see in the following slides, the process is recoverable, and if you let temperature anneal the melt is gaining in viscosity, and try to return back to a stable value which has a higher viscosity, not a lower viscosity. So if you had it plasticized, it would not be a reversible effect. Same thing for branching. If you have some branches, and sometimes you do create branches, it would still limit the value of the lower viscosity, the Newtonian viscosity, but not if a melt is capable of going back to its initial viscosity. So it would not explain that. So this is not a recoverable viscosity if you have created plasticizing oligomers, for instance, or if you have some branches. But this also does correspond to partial explanation of the results, and we need to investigate and to break down the fluidity increase into its different compartments. Now let's look a little bit. As I said, this melt is not stable. For instance, here this is a polycarbonate melt, and the black curve is a disc which has been molded after the pellets, which were collected at the end of the double rheofluidizing treatment, and and compare that with a virgin, which is also the same curve as the red curve, which is obtained by letting the melt rest at the rheometer at the high temperature, so that if it is in non-equilibrium, then we hope to re-establish an equilibrium. And as it turned out, that melt didn't have a change. The treated melt, if you want, the first pass, is the same as far as the Newtonian viscosity. So the melt flow index is unchanged, and therefore you might think, well, we have done nothing to the melt. Well, on the contrary, if you compare the red and the black curve, you see that the melt shear thins much more. That means its pseudoplasticity has increased tremendously. If you compare at 2000 strain rate, the value of the viscosity, the log of viscosity for the red and the black curve, this is huge. So in an injection molding machine, for instance, you would benefit quite a bit from the black, melt. Of course, this black melt, if you let it stay too long in your machine, it will return to the red curve. This is what's happening here by doing two frequency sweeps, one after the other, and waiting a certain holding time at temperature. Actually, what we do is that these curves are obtained at 225 polycarbonate, and we go to 275 for 5 minutes, and we see that the melt is returning to the virgin value, the virgin curve. Here, same, but I am showing the little difference in that the Newtonian viscosity is different. As you can see, the black curve, which is after the treatment, the Newtonian viscosity is lower, and the pseudoplasticity is also lower, is increased, sorry. But if you the original melt, if you compare it to the original, we see that it is the MFI value would be less, and the pseudoplasticity is also improved for the after treatment. But as I said, you go back to 275 for 5 minutes, and of course after also having all this heating to the pellet to make discs in a compression mold, and then another heating in the rheometer itself to reach the temperature of 225. All this at the end, you're recovering and recovering and recovering. This is what's left. Now, if I compare on this graph, which normally is at 225 degrees C, and these are different treatments through the coupled dual processors. The black dot that square that you see in the middle are the original frequency sweep for a virgin sample. As interesting as you can see, there is not a single curve. After treatment, you have destabilized the entanglement in the melt, so that you have a series of curves. Actually, you cannot recover, by shifting alone these curves into a master curve, so that the idea that you could use a ME like in a kind of a Vinogradov plot to scale the viscosity axis and the omega axis by multiplying or dividing by ME is not correct. You cannot do that to obtain a master curve. It's much more complex. You would need also to tilt the curves, rotate them, which implies a definition of ME, which is very different from the one used in linear viscoelasticity. More in a minute in my conclusions about that. If you compare the values, for instance, at the high omega, this is just incredible. It goes from 3.4 in the log scale for the viscosity to down to 2.9. Okay, So it's a huge difference that describe these curves. And more is that you see curves which are on top of a virgin, showing a higher viscosity than the virgin. So I'm boosting the viscosity and the elasticity of a melt by the process. I can obtain lower viscosity or higher viscosity. So the instability of entanglement goes in both directions. It's like when you orient a melt, you can compress or stretch. Here, same. You can increase viscosity with respect to the equilibrium value, or you can decrease the viscosity. And this is also a function of the speed. In other words, the shear thinning, the pseudoplasticity, is affected by the changes of the state of the melt. I am showing the re-entanglement, so-called, of PMMA in the rheometer because this was rather exceptional. The black is the disentangled sample, so this is created from the pellets which were turned into discs, which were studied in the rheometer, and with a frequency sweep, you see some kind of a activity at the low end of omega, where you see the melt is trying to return to a higher value, but this is compensated by shear thinning, and now you have to wait 24 hours at 230 degrees C under nitrogen. There's no degradation. Well, the degradation would actually decrease viscosity and not increase viscosity. But to obtain the red curve, what I call annealing, it was done, and amazingly, it took 24 hours for the melt to go back to its original viscosity. So this is incredible. 24 hours, which, as we saw, the tau d, the reptation time, is 5 milliseconds. So we are dealing with a phenomenon which is not described so far in the literature in polymer physics. As I said here, the recovery for PMMA took 24 hours. Tau d is 5 milliseconds. Observations are not due to molecular weight changes, as tested through a SEC GPC, although processing for long times at high temperature, and especially when there is no nitrogen flowing, has collateral damages. So we know that when there are molecular weight changes, we know how to correct it. This is what I say in the last paragraph. At high shear, high processing temperature, some degradation occurs, which can be intense for some polymers, for instance polyolefins. But when corrected for degradation, large recoverable viscosity reduction are still observed. So this has nothing to do with topological changes, although topological changes may occur, do occur, and influence the results. Okay, sometimes overshadowing the results that we want to obtain. At low processing temperature, there's no degradation at all. For instance, if I use the viscosity reduction to lower the processing temperatures in all the zones, including the zones where the melt is flowing and is not being treated, I can do that. I can lower temperature to an extreme. For instance, here I can process this PMMA to approximately 150 degrees, okay, instead of 230. And in that case, I do not see any degradation of molecular weight at all. I'm reaching the conclusions. The pseudoplasticity of a treated resin can be varied by rheofluidification, as well as the value of the Newtonian viscosity, which is, as we know, the inverse of the MFI. As the melt of a treated resin is annealed at high temperature, frequency sweep tests show a gradual return to normal pseudoplasticity and normal Newtonian viscosity. Of course, when there is some degradation, the so-called normal Newtonian viscosity is lowered. But we know that from viscosity the degradation is affecting the viscosity, and we cross-reference that with a GPC study. Sustained orientation is totally incomprehensible in terms of our present understanding of entanglement, the cornerstone of long-chain physics. That's a fact. I'm describing things which are not described anywhere, and I've been in polymer science for quite a long time, and I have spent the last 5 years trying to understand those results with the present current established views. And to me, this is challenging the views of the current understanding. There is no explanation in the current theories for an unstable entanglement network. So it's a new idea that I'm saying, is that the network itself has to be defined, and it's not a classical network of physical points. This is a different state for the network, and that network can be modified, can be mechanically treated so that it becomes unstable, and the liquid state which corresponds to it is no longer at equilibrium, and the importance is to determine why mechanical stresses, therefore deformation or history of deformation, like I've shown in the dual real fluidification processors, how does it this type of deformation triggered by nonlinear viscoelastic conditions, why does it create sustained orientation? Why does the network of interactions between the bonds, between the conformers, has become so stable that even when we are 125 degrees above TG, it takes 24 hours for the network of bonds to re-establish itself into a stable, classical network of entanglement? What is going on? Conclusions. In this presentation, we've described processing conditions which trigger melts to behave in novel ways, challenging the currently admitted models of polymer rheology. The viscosity of a polymer melt could be greatly reduced, and the reduction of viscosity maintained at high temperature for times 100,000 to several million times greater than the longest relaxation time. The instability of a network of entanglement could be induced by coupling, shear thinning, and strain softening in what we described a Rio fluidification processor, which we use to disentangle quote-unquote polymers, subsequently re-entangle quote-unquote in different specific ways, creating new exciting materials. I will describe in another forum, another presentation, how we can create new exciting materials by modifying the entanglement network and recombining the network into something which is favorable, such as batteries for plastics, mechanical batteries where the deformation is sustained and the deformation is released in time, triggered by temperature, by thermal activation. And this is another subject, but I am saying here we can create by extrapolating this concept to new ideas, we can create exciting new materials. So sometimes, and we're going back to the first slide, Trouble with Physics by Smolin, sometimes a dominating concept can prevent people from going to the edge. The edge is not broad enough. It's the frontier of science has to be exploded, and we can here think of new experiments which, if you were to follow the current established models, it would be no, you can't do it. because there is no explanation to it, and you're wasting your time and wasting money. Polymer melts are not simply defined by their reptation time, tau sub d, or by a scalar representing the network of entanglement, m sub e. These are useful parameters when the liquid state is in equilibrium. For instance, in their conditions where the linear viscoelasticity is used, the melt remains in equilibrium. There's no question about it. These are useful concepts. This has been demonstrated for the last 40 years. But my conclusion is that non-equilibrium liquid states can be generated by rheofluidification, stabilized by sustained orientation. In other words, I can stabilize the melt in another new way by use of mechanical deformation in a nonlinear viscoelastic regime, which creates non-equilibrium liquid states. We suggest by this research that we need to revisit our understanding of a concept of entanglement in polymer physics. And I'm going to close with this idea about entanglement. For instance, a very good book that students learn rheology from is Rheology Principles, Measurements, and Application by Makosko. Chris Makosko is the editor of this wonderful book, published in 1994, and chapter 11 is a fantastic chapter from Professor Tyrrell, and in that chapter defines entanglements, and he has this sentence which has its merits. The folklore of polymer science, it defines entanglements. I have to say that I found it funny and interesting, especially in the view that I want to introduce new concept of entanglement, but at the same time I have to disagree. This is not a folklore of polymer science. This is a difficult concept to coin. This has been for a long time. Science in polymers has existed for 80 years, and it has been derived, the concept of entanglement, from physical chemistry, from cross-linking, from vulcanization of rubbers, and from essentially physical entanglement. And this is not folklore. The attempt to describe it with the new concept of reptation from De Gennes was a very interesting idea. I say was a very interesting idea because I believe that it was an attempt to understand entanglements, but in my opinion it failed because it used topology, it used the tube, it used the molecules themselves to define the interactions. It used the mean field theory to describe interactions between molecules. So as I will now quickly describe, I am introducing in this series of lectures a new school of polymer physics which with the following objective: a new understanding of polymer properties based on a different concept of entanglements and melt entropy. And I have already published and focused in the following understanding: local motions, for instance, coming out of DMA, tension delta versus temperature at a given frequency, 1 hertz, say, or infrared, or spectroscopy, or spectroscopy itself, dielectric or mechanical creep, viscoelasticity phenomenon, linear and nonlinear, the effect of strain percent in a radiological instrument, or Laos in rubber elasticity, the plateau, the existence of a plateau, the length of a plateau as molecular weight increases, the fracture effects especially the onset of physical fractures such as shark skin, and also the influence of crystallization on the network, on the entanglement network, and how these are related and interdependent. So these I have already described in lectures, in papers, and in teachings, and I am of course writing a lot about it in a book which will summarize this work. It's just a beginning, but it sounds like I am capable, for instance, in linear and nonlinear viscoelasticity, of introducing very, very different concepts and arrive at describing experimental results which are the common known frequency sweeps or temperature sweeps observed by the students. So if the same phenomenon can be described by two different opposing views of entanglement, one has to wonder which is the view which is capable of understanding most of the facts. That's science. This is the duty of science. Okay? And I am introducing a new model of interactions, of the van der Waals interactions, basically, between components of molecules, which I call conformers, and although the statistics is broader in scope, I'm applying it first to polymers and the grain field statistics. I'm considering all the macromolecules at once. In other words, all the conformers from all the macromolecules are defining the system, and I am granulating the system by not considering the field of interactions as a mean field. It is a granular field which explains, or and I will show it, that the concept of a ME is not inherent to the molecule, the macromolecule itself, but by the interaction between the macromolecules through the grain field statistics. And the grain field statistics in this particular understanding of the interactions explains a split of the system into two dual phase systems, the cross dual phase, which appears to describe very well many of the observations that I see above TG and below TG at all macromolecular length. So not only do I need the concept of macromolecules, because otherwise I would not see what I observe at ME, but I can also say that there is a critical molecular weight for the interactions in the grain field statistics, where I need to split the local dual phase system, which normally does apply at lower molecular weights, at low molecular weight or low number of bonds of conformers in the system. But as the number of bonds in the systems, interpenetrating systems, interacting systems increases, I have to define and see some changes which are considerable, have considerable consequences on the behavior of the interactions, and that is what I ascribe to the molecular weight for entanglement. Obviously, this is totally different from what has been presented to this view, to this day, and that's why I think that the exploration of this and the improvement of the model, can be confined into a new school of polymer physics understanding. This is a little sketch. I could end, with a closing statement, but here I have, shown two different concepts of entanglements, which are obviously sketches, and therefore should be described by equations and mathematical model. But the cross dual phase model view of entanglement looks more like the interpenetrating network of two states of the liquid state of interactions, which can be characterized by their free volume are different, slightly different, and their conformational statistics of the MERS, the conformers, is different in both, but they are lying as interpenetrating networks as shown here. And actually this is a picture of a carpet in Biarritz, which is facing the ocean, and of course one will recognize that is supposed to represent the ocean with the wave and the foam from the waves, creating this network. Okay, the rotation view of entanglement is taken here at the bottom of this slide from the famous book from De Gennes, Scaling Concept in Polymer Physics, I think it's called. For those who love to read titles which are a little controversial, I have written and I'm continuing to write this series of articles, The Great Myths of Polymer Rheology, and I have reached part 4, part 1, 2 and 3 being published. This represents a about 300 pages of description of experiments in rheology, where I do express my concern that some of the experiments are not considered by the current theories. And I also, in part 3, reference 3 here, I describe the new parameters that I use to study linear and nonlinear viscoelasticity. So I give a different interpretation of shear thinning, of diffusion, and of strain softening in polymer materials. In the number 4 and 5 you will find a simple flow simulation and description of what I've shown and talked about today, the rheofluidification and the machinery to describe that, the experiment of the first type, and then an example, simple example of use of a rheofluidification processor to mix polymers. And as you will see, this is a very good machine to do that, to create actually intermolecular interpenetrating networks. Since I'm contending that I can do that with a homopolymer, I can indeed obviously try to do that and modify it and create a fantastic interpenetration for PET and polycarbonate, for instance, which I've done, or different molecular weights to create a polydisperse curve of a known characteristic, which is beyond what chemistry can do, by blending a different molecular weight monodispersed, and obtained an interpenetrating network with a homogeneous stable entanglement network with a molecular weight distribution of known characteristic or desired characteristics. It goes on and on. You will see it through the different classes in this course, but here I'm giving some links for the blog, New School Polymer Physics, New School Polymer Physics blogspot.com. Also, there are 23 classes already downloadable in the WYSIQ.com platform, teaching platform. And then the Greenfield statistics sites has just started to pop up some of the links explaining dual split statistics and its history, and how it came about to this point, and the mission and objectives for the Greenfield campus, which I hope you will be interested in joining. So I am saying thank you in Basque, Esquerigasco, and the acknowledgement of his work was made possible through several grants, and I'm thankful to a Fulbright Foundation, the Icar Basque Academy of Science Foundation, and a Marie Curie grant. This presentation was recently made as a keynote presentation in the rheology section at the PPS, Polymer Processing Society meeting in Nuremberg in Germany. So this last July.